Hi everyone. Today we're going to be continuing our notes in 3.2 on polynomials and their graphs, and I want to talk about using zeros to graph the polynomials. We'll start with this idea of roots. The real roots of a polynomial are where the graph of the polynomial touches the x-axis. This is the only location where the output values of a polynomial can change signs. So when we talk about roots or zeros or x-intercepts, know that these concepts are pretty synonymous. We also know that this is the only location where the outputs can change signs. So, of course, it follows that if the x-axis is y equals 0, then as a polynomial function, or really any function for that matter, crosses through the x-axis, then it's changing sign from positive to negative or from negative to positive. So I want to start off with this definition here. Let f of x be a polynomial. If r is a real number that satisfies any of these following four statements, then r satisfies all of the statements. The statements are that r is a zero of the function f, r is an x-intercept on the graph of function f, x equals r is a solution or a root of the equation f of x equals 0, and x minus r is a factor of the polynomial f of x. Okay, so let's apply some of this knowledge. Let's find the zeros or the roots of y equals x squared minus 7x plus 10 by factoring. We're going to sketch the polynomial function below and label the zeros, the roots. So if I were to factor this, I'm looking for factors of positive 10 that add to negative 7. Those factors are negative 5 and negative 2. So this factors to y equals x minus 5 and x minus 2. Using our definition from above, that tells us that we have roots at positive 5 and positive 2. Think about the zero product property. If we were to set y equal to 0, or in other words, find the x-intercepts, then each of these factors, x minus 5 and x minus 2, would yield solutions x equals 5 and x equals 2. So let's go ahead and plot those on our grid here. So we have x equals 5, x equals 2. I also noticed that the y-intercept, where x equals 0, is 10. So let's go ahead and label that as well. Okay, so what we have here is a quadratic with a positive leading coefficient, so it opens upward. And so I'm just going to sketch this graph. Remember, a quadratic is that U-shaped graph. And it doesn't have to be perfect, just get the general shape of the graph. It's U-shaped, it opens upward. Both ends are going up, and we've got those intercepts, a y-intercept of 10 and x-intercepts of 2 and 5. The degree of this function, this is a quadratic, so the degree is 2. The number of zeros, roots, or x-intercepts, that is 2. The number of distinct real zeros is also 2 because 2 and 5 are distinct from one another. And the multiplicity of each zero is going to be 1. So I want to go ahead and define that word multiplicity. Multiplicity of a zero is the number of times that a factor occurs within the factorization of a polynomial. So when we're talking about the factorization here of this quadratic, we see that each of these factors, x minus 5 and x minus 2, each occur exactly once in the factorization. So let's determine the end behavior, or determine the term, the dominant term, that best models the end behavior of the given function. Well, we know that the dominant term in this quadratic is going to be that quadratic term, x squared. So that tells us that the limit of f of x as x approaches negative infinity is going to be that of x squared, which is positive infinity. And then the limit of f of x as x approaches positive infinity is equal to infinity. Now I want to draw a sign chart to verify the intervals for positive and negative values graphed above. So a sign chart is, think of it similar to a number line. It's just intervals for which the function is positive or negative. We construct this by labeling each of the zeros on the number line. So I notice we have zeros at 2 and 5. And I know that both ends of the function are going to approach infinity. Therefore, for everything less than 2 and for everything greater than 5, the function is going to be positive because we're approaching infinity. I also know that between negative 2 and 5, the function is negative. And so at those zeros, it changes sign. So we go positive, negative, positive about those zeros. All right, go ahead and flip the page. Let's try number 2. Find the zeros or roots of this polynomial. This is another quadratic. We are going to factor this one. So I notice that this factors to y equals x minus 2, the quantity squared. Or you can think of factors of positive 4 that add to negative 4. Those factors are negative 2 and negative 2. This factor occurs twice. The degree of this function is 2. This is a quadratic. The number of zeros, we have 2 zeros. Because this is a quadratic, degree 2, we have 2 zeros. And the number of distinct zeros, in this case, we have one distinct zero, and that's going to be x equals 2. The multiplicity of each zero is going to be 2. All right, so let's go ahead and graph this. Here we have an x-intercept of 2, and we also have a y-intercept of 4, and that's from that constant term. So let's go ahead and sketch this graph. We're going to go up. Because this leading coefficient is positive, we know that this opens upward. Okay, we've only got that one distinct zero. It's only going to touch the x-axis once. Okay, determine the dominant term of this function. Well, the dominant term is again going to be that quadratic term, so x squared. So we can determine the end behavior of this function. So the limit of y, or I'll call it x squared minus 4x plus 4, for x approaching negative infinity is equal to positive infinity. And then the limit of x squared minus 4x plus 4 as x approaches positive infinity is equal to positive infinity. So let's go ahead and draw a sign chart. So we have 1, 0 here, and that is at x equals 2. We know both ends of the function are going to be approaching infinity, so for all the values greater than 2 and all the values less than 2, it's going to be approaching infinity. It's going to be positive. Okay? So one thing that I noticed is different between example 1 and example 2 is that in example 2, x equals 2 is what we call a point of tangency. Tangency just means that it intersects exactly once. So when we're talking about the function, it intersects with the x-axis exactly once at this point. Or in other words, this graph bounces off the x-axis at x equals 2. The graph is changing from decreasing y values or decreasing outputs to increasing outputs at the x-axis, where that minimum value is the x-intercept. Okay. This brings us to multiplicity, which I mentioned earlier is the number of times a factor occurs within a factorization of a polynomial. So let's come up with a definition here. Let C be a zero of multiplicity k of a polynomial f. So remember, if C is a zero, then x minus c is a factor of the polynomial f. And if it has multiplicity k, we're saying that that factor occurs k times in the factorization. So we can raise that to the power k. If k is odd, if the occurrences is odd, then the graph of f crosses the x-axis at c. Okay. We also know that if it crosses the x-axis, it's going from positive to negative or from negative to positive. So therefore, the output of the sign of the output changes. Okay. If x is even, then we have an even number of occurrences of this factor. Then the graph, this would be similar to example 2. Then the graph bounces on the x-axis at c. The output, the sign of the output, I should say, stays the same. So as we can see above with our sign chart here, at x equals 2, the sign about this 0 stays the same. We're staying positive. We're not flipping over that 0. All right, so let's try a few more examples. Flip the page. Number 3, determine the intervals that the polynomial here is positive and negative. So I want to start by just finding the dominant term. In order to find the dominant term, we have to know the degree and the leading coefficient of this polynomial. If I were to factor or multiply this out, we would see, well, I have 1x right here, and I have 2x's right here, and then we're multiplying everything by negative 3. So that tells me that my dominant term is negative 3x cubed. We've got 3 x's there. Okay, so that tells me that the end behavior of the function f of x is going to follow the same as that of negative 3x cubed. So we have the limit of f of x as x approaches negative infinity is going to be negative infinity. And the limit of f of x as x approaches positive infinity is going to be infinity. So think about the shape of a cubic function. It's rising, generally, I should say, from left to right. So as we move to the left, the function is decreasing. As we move to the right, the function is increasing over all real numbers x. So list all the real roots of f and state the multiplicity. Well, I know that because it's factored, we can use its factorization to find its roots or its zeros. So we have x equals 4 and x equals -1. Okay, so looking at the factorization, the multiplicity of the 0 at 4 is 1, right? This factor occurs once. For the factor at -1, this factor occurs twice. And I always like to do a double check, add up the multiplicity of all of the zeros in your, or all of the roots of your factorization, and make sure that it adds up to that degree of the polynomial. So because we have one multiplicity 1 for that factor at 4 and multiplicity 2 at the factor at -1, we see that those add to 3. So that's a good quick check to make sure that you've accounted for all of the zeros. So let's go ahead and use the sign chart to determine the intervals for positive and negative values. So again, we have zeros at -1 and at +4. So I know that the function, the left-hand end behavior is going to be negative. So all the way up to -1, it's going to be negative. At -1, we have an even multiplicity, so it's going to bounce. So the sign stays the same. So it's going to be negative between -1 and 4. And then at 4, the multiplicity is odd, so it's going to pass through. So then the sign is going to change. And I just want to double check that everything greater than 4 should be approaching positive infinity, and it is. Okay, so that's a good check to see that we've done our sign chart correctly. Okay. Number 4, determine the intervals that this function is positive and negative. Okay, so I need to know the dominant term here. And number 4, we've got 1x here, we've got 2 right here, 3 right here, and 1 right here. So that tells me in total we have 7 x's, and then we've got a leading coefficient of 2. So then the dominant term is 2x to the 7th. Okay, this is a polynomial of odd degree, so that tells me that the limit of f of x as x approaches -infinity is going to be -infinity, and then the limit of f of x as x approaches positive infinity is going to be positive infinity. So the real roots of f and stating multiplicity, well, we look at each of the factors. So we've got that x minus 3, x plus 1, and x plus 4, but don't forget that first factor as well. That has a variable in it as well. So that 2x is a factor, and that yields the solution x equals 0. Remember the zero product property, set all the factors equal to 0. So then we also get x equals 3. We get x plus 1 equals, or you know what, let's go ahead and solve. We have x equals -1. We have x equals -4. So these are all of our distinct zeros. At x equals 0, the multiplicity is 1. This 0 occurs once. At x equals 3, the multiplicity is 2. At x equals -1, the multiplicity is 3. And at x equals -4, the multiplicity is 1. And again, I'm going to do that check. Does 1 plus 2 plus 3 plus 1 equal 7? Yes, it does. So we've accounted for all of our zeros. Okay, so let's go ahead and use the sign chart. And I'm going to plot each of these zeros. So we have -4, -1, 3, or 0, and then 3. Okay, so the left-hand end behavior is going to be negative. We're approaching -infinity. At -4, we have a multiplicity of 1, so the sign is going to change over that 0. At -1, we have a multiplicity of 3, which is also odd, so the sign is going to change there. At 0, we have an odd multiplicity, so it's going to change again. But then at x equals 3, we have an even multiplicity, so the sign is going to stay the same there. And I always do that double check. Is the right-hand end behavior positive? Yes, it is. Okay. Number 5, determine the intervals that the polynomial g of x is positive and negative. We want to use that dominant term rule again, and I notice that the dominant term here is -2x cubed. So that tells me that the limit as of g of x as x approaches -infinity is going to be positive infinity. We've got that negative leading coefficient. And then we have the limit of g of x as x approaches positive infinity is going to be negative infinity. So let's go ahead and factor this polynomial. We're going to go ahead and use the TI Inspire to factor this. So if you have yours, go ahead and take it out. And once you're in there, go ahead and open up a new document with a calculator. To factor a polynomial in the Inspire, you can just go ahead and use the factor feature. You can type it out like this, or another way to find it is you go to Menu, you go to Algebra, and then Factor, number 2. Okay? And so now let's go ahead and type in that polynomial here. We have 1 minus 3x squared, and then minus 2x cubed. Okay? I'm going to hit enter, and it gives us the factorization. -1 times the quantity x plus 1 squared times the quantity 2x minus 1. All right, so let's go ahead and write that. We have g of x is equal to -1 times the quantity x plus 1 squared, and then times the quantity 2x minus 1. So that tells us if we take each of these factors and set them equal to 0, we have solutions x equals -1 and x equals 1/2, where the multiplicity at -1 is 2, and the multiplicity at 1/2 is 1. And again, we've got 3 zeros here, and all the zeros are accounted for here. All right. Go ahead and flip the page. So now I want to use the sign chart. This actually follows from the last one. So if I wanted to use a sign chart, we've got our zeros at -1, and we have one at 1/2. The left-hand end behavior is positive. The between -1 and 1/2, at -1, we have a multiplicity of 2, so the sign does not change. It bounces at -1. And then at 1/2, the multiplicity is odd, so it flips sign. And again, that follows with our right-hand end behavior. Okay. All right, so number 6. Here we have a graph of a function, and I want to determine some of these characteristics of the function. Is the degree of g of x even or odd? Well, let's count the zeros. I notice that we have a 0 at -2, a 0 at 0, a 0 at 4, and a 0 at 6. Now, I notice that 3 of these zeros pass through the x-axis, but the 0 at x equals 0, the root at x equals 0, bounces. So that tells me that that factor has even multiplicity, or that that factor occurs an even number of times in the factorization of g. So this tells me that if we have 3 that have odd multiplicity and 1 that has even multiplicity, that tells me that the degree of g of x must be odd. Okay, very likely this has degree 5, because we have 3 odd. Those are probably 1, and then this one has multiplicity 2. So we've got 3 and 2 gives us 5. So it also follows from the end behavior. Left-hand side is going down, right-hand side is going up. So leading coefficient, left-hand side's going down, right-hand side's going up. That tells us odd multiplicity or odd degree, tells us that this has a positive leading coefficient. Okay, so the zeros, we said that we have one at x equals -2, x equals 0, x equals 4, and x equals 6. So multiplicity of each of these zeros, we have 1 at x equals -2. At x equals 0, that's where it bounces, so that's multiplicity 2. Multiplicity 1 for x equals 4, it passes through, and multiplicity 1 for x equals 6, it passes through again. Okay? So the smallest degree of x, if we say that the multiplicity is, I should really say these are odd and even, right? So we're assuming that it's 1 and 2, and that's the minimum that it could be. But know that this has to be odd, and then even, and then odd, and odd. So then the smallest degree would be 5th degree. Okay, so the possible factors would be g of x is equal to x plus 2, and then we have x squared, or x minus 0, the quantity squared. So I'll put an x squared out front. We've got x minus 4 and x minus 6. Okay, So this is a possible factorization. All right, so we've got one more for today. Number 7, a sign chart for a polynomial h is shown below. The roots of h are -3, 1, 5, and 9. The degree of h is 5. So is the leading coefficient of h of x positive or negative? Well, I know that the degree is 5, so that tells me that the end behavior in both directions is going to be opposite, one up, one down. And I notice that the left-hand side is approaching negative infinity and the right-hand side is approaching positive infinity. So that tells me for an odd degree polynomial that the leading coefficient is positive. Okay. Multiplicity of each zero, I see that we have one at -3, we have one at 1, we have one at 5, we have one at 9. The multiplicity at -3, well, it looks like it changes sign here. So this is going to have multiplicity 1. At x equals 1, the sign does not change, so that must be an even multiplicity of 2. At x equals 5, the sign changes, so we have a multiplicity of 1. And at x equals 9, we have a multiplicity of 1. The sign changes. And just to be sure, I count up all these multiplicities, and it does add up to 5, which is defined for h as the degree. So a possible factorization would be h of x is equal to x plus 3, and we have x minus 1, the quantity squared. We have x minus 5, and x minus 9. Now, one thing I want to note is all we know is the x-intercepts. We don't know whether or not there's any vertical stretches or compressions to this function. So we don't know what the y-intercept is. So I'm going to put a big note here. This could have multiple functions with the same zeros. Right? We don't know anything about what's going on with the graph vertically. We only know horizontally with these x-intercepts. Okay? So these have been our notes on 3.2, using the zeros to graph polynomials. We're going to get a lot of practice on this in class, so we'll see you tomorrow. Have a great day, everybody. Goodbye.